Okay, now to one of the best subjects in chemistry, the periodic table. Of course, this is wonderful stuff, right? You all know what a periodic table looks like. If not, I highly advise a website that I very much enjoy called ptable.com, and it's an easy way to refer to a periodic table and get a lot of information off of it very quickly. So, periodic table, we put this together, or not we, but scientists put this together before we even knew what all of the elements were. But an element is represented as a block on the periodic table. So if I pull over an example that just happens to be on my desk right now, this is obviously much too large to get on here. You see all of these blocks is representative of one element. Elements are pure substances, they're specific atoms, and everything in the entire universe that has mass or takes up space, occupies space, is an element on the periodic table or involved in chemistry somehow, okay? And the periodic table can tell you a lot of information if you know how to use it. And so that's what I'm going to try to teach you all how to do. When you do abbreviations for different symbols, they will start with a capital letter. So F, for example, is fluorine. ZN would be zinc. See how the second letter here is lowercase? That's very standard if you have two letters in an abbreviation, and those are called chemical symbols. Okay. So Dalton basically envisioned that there would be something that would be termed an atom. If you kept dividing things, eventually you would get to the point where an atom would be indivisible. And though that's not completely true, because we know that there's parts of an atom, it's rather that we know with an atom that it has all of the parts that would be of, like a representative of that element, okay? So, the smaller particles that make up an atom are threefold. An electron. Electrons have a very tiny mass. They're teeny tiny things. And as a matter of fact, you almost can consider electrons as energy. It depends on how you measure that as to what it really looks like. So they're tiny, tiny things that are somewhere in the realm of mass versus energy, depending on how you view things. And they have a charge that is negative. So a negative charge, okay? Protons are much heavier than electrons. They have a positive charge. And then there's this thing called a neutron. Neutrons are as heavy as a proton, but as their name indicates, they are neutral, so they're not going to have any charge. There's some ways that we have looked at different types of experiments to show us information about these subatomic particles, okay? That's what those are called. Subatomic because they're smaller than atoms, particles, okay? They're tiny, tiny things. Okay. I'm going to skip through that right now and just talk about the reality of using this information. So this is a good chart to sort of think about things in. And when we talk about mass of an atom, we can talk about it as a group, like a big, huge, massive amount of atoms together and average that. Or we can talk about an atomic mass unit, or AMU. And that's usually in reference to a particular atom, okay? So what we said is this AMU is about the same mass as a proton. Now, the cool thing about that is that a neutron has about the same mass as a proton. So relatively speaking, they both have one mass, versus an electron is so small in comparison, we just consider that zero. Remember that a proton charge is +1 and an electron charge is -1. Okay. So how do we use that information? Well, on a periodic table you'll have something that looks like this. We can see it this way on a periodic table, or another way to look at that, pardon me, I'm going to move this, is like this. When you're talking about a specific isotope or a specific number of neutrons within an atom, then we often refer to things simply as this. This is more specific because this says, hey, I've got exactly 9 in beryllium. Now let me go back and talk to you about what this means, okay? See how this says 9.012. This is the mass of all atoms of beryllium in the universe. Okay. This is the atomic number. The atomic number tells you how many protons there are in beryllium. You can change, let me repeat this, this is very, very important, okay? You can change the number of electrons or neutrons in an atom, but you cannot change the number of protons in an atom, because if you change this, your atomic number changes, and instead of being number 4, that becomes number 5, and it's a different atom. Okay? So that means that this number up here is defining that this is beryllium, and that is your atomic number. That atomic number tells you that you've got 4 protons. Okay? Now, that's going to be the same as the number of electrons if your beryllium is neutral and you don't have a charge to it. If you haven't seen something with a charge yet, you don't have to worry about that yet, because there's not going to be one there, okay? But this number down here, it's not a whole number. What it's actually representative of is all the average mass of all beryllium atoms. Remember how I said you can change the number of neutrons, and neutrons have charge? Or, I'm sorry, not charge, excuse me. Neutrons have mass. Well, if you have different types of beryllium atoms that have different numbers of neutrons, that's how you can end up with having a larger amount here or a smaller amount. So when this is said that it's an average, it's not that you have 0.012 of a neutron hanging out somewhere. It's that if you have a whole bunch of beryllium atoms, what we find is their mass on average is 9.012, because there's probably a little bit that's going to have a mass of 10 instead of 9. Okay? So here's how we figure out how many protons and electrons and neutrons. We just said that you've got protons is right there. If it's a neutral atom, that's the same thing as you're going to have with your electrons as well. Now we have to go to sort of one of these views to be able to tell what's going on for neutrons. Okay. A lot of times we just sort of round that up because you can't have a part of a neutron. But all you have to figure out for neutrons is, okay, my atomic mass is 9. My atomic number is 4. This tells you how many protons you have. So 9 minus 4 is 5. So that's how you know how much mass is contributed from neutrons. Okay. Okay. Isotopes, what that term means is that you have the same element with different number of neutrons. If you have a charged atom, you're going to have a different number of electrons. Okay. But notice how here these numbers are backwards in comparison to what's on the periodic table. Yeah, I don't know why they did that, but they did that. So that's just to basically identify which isotope you're talking about. So, math. The same way you can identify how many neutrons are in any given isotope of a compound. So see here, like neon, this one has a mass of 20, this one has a mass of 21, this one has a mass of 22. If we wanted to determine what the overall average mass was for all of neon, we have to look at their mass in AMU and see how those are different. They differ by 1 because that's going to be an extra neutron in each of those. Remember, protons stay the same. And we look at what their abundance is. So this is their percent abundance. So 90.92% of the time, neon is in this form. 0.25% of that time, neon's in this form. 8.82% of the time, it's in this form. So all we have to do is divide each of these by 100 to give a relative of one universe rather than 100%, okay? And multiply it by this value. So 19.99 times 90.92 divided by 100 is going to give us a value. We do the same thing here and the same thing here. And then you average that together, or another way to look at it is right here. And this gives you 20.17 as the overall average mass for neon. Something to keep in mind is you still have to take into account significant figures. And the other thing is you can look on a periodic table if you're given one and determine exactly if that's somewhere close to right. It may be off by a few numbers at the end, point something like that, but that's okay. Okay, thank you.